Yeah, hello everyone. We are the group predicting learning outcome supervised by Professor Ken Codinger.
Thank you. This is second years, right?
Just fill
Okay,
in
so
and figure out
so educators have been always concerned by how to understand the related factors about students' learning outcomes and how to improve their ability to uh,
There was
learn.
supposed to be food,
And we
but
aim to
some issue was
develop
on morning, so
a
I don't know.
robust model to predict students' learning outcome, and we
Okay,
hope
yeah,
that our
just
research can
Is this still available?
result in better improvement of
Maybe it's
online
fine.
learning platforms.
yeah. So what do you
So
say?
our goal is to basically predict students' learning outcome using regression models. Um, we have to answer three questions to achieve this goal. The first is to how can we predict student learning outcome using students' past learning experiences. And the second one is for teacher and school that can influence on students' opportunities. How can we provide better factors and provide support to student engagement in the classes? And for the third question is, given the exploratory benefits of logistic regression models, how can we understand reuse the whole process to develop a pipeline for easier analysis? So the main data set we are using is the Bernanke data set from the DataShop platform. And the primary model we are going to use is the mixed effect logistic regression model.
Share them so much.
Yeah.
You're not sharing your slides. Oh, yeah. Yeah, it's good.
Okay, so there's some previous related work, and on this part. So we have two hypotheses. The first is the learning opportunities experience are the primary factors among those that can be changed in predicting student learning gains. And the second one is how each factor interact with each other can affect the student's learning outcome. We have four major features for our project. The first one is the statistical model, which is built in R. And the second one is the model comparison analysis between those models. The third one is the workflow component deployment on LearnSphere, which is a platform to provide learning experiences. And the first one is to automate the process for pretest and post-test for extractions.
So I'll go over quickly about our intended users. So our intended users include educators, learning scientists, software designers, parents, and students. So we hope that our analysis results can provide some insights for those educators and learning scientists to develop more efficient courses. And for software designers, as we will be deploying our whole pipeline on LearnSphere, this might give them some insights to develop more components on that platform. And for parents and students, they might know that what are some of the important factors that will help them get better performance in their studies. So for system functionality, we have data management, prediction output, systematic workflow component, and reporting. So we will be dealing with a lot of data sets, which are all related to the students' learning behaviors. So we hope to manage the data into a systematic way so that later users can approach our data set more easily. And for the prediction output, so we are using the regression models to do the prediction. We hope that we can store our prediction output in the forms and it can be approached later for use. And we are also planning to deploy a workflow component on LearnSphere so that the whole pipeline can be reused. And we will also be reporting our results. So for the non-functional requirements, we have confidentiality, reliability, scalability, and fairness. So for confidentiality, we confirm that our data are all confidential and will not be shared for third-party uses. And we are also sure that our models are reliable and consistent across different data sets, and we will be providing different evaluation metrics for evaluation comparison. And our model are able to scale across different data sets and will not be biased according to different genders or ages. So the resource we are using, so for the data, we are using the Bernanke data set and also the DS 4555 and 5165 on DataShop, and also 3093 and 3151 on DataShop. And for the computation power, we will be mainly using the GCP and Google Colab. So here's our design overview. So our design consists of 5 parts: data processing, feature selection, modeling, advanced analysis, and workflow component deployment. So for each of our input data, we'll do a data processing, including the data cleaning, feature engineering, and coding. And then we'll put into the mixed effect logistic regression model. And then after that, we will do the result comparison and analysis, and also deploy the whole pipeline into a workflow component on the LearnSphere platform. So as I just mentioned, we want to pack our whole pipeline as a tool on LearnSphere so that later researchers can reuse. And this tool is to simplify the whole process. So for researchers who do not know R, they can use this tool to get the results for their own analysis by simply choosing the data set that they want to analyze and then get the results. And for users who know R, in this tool can avoid writing repetitive code and automate the whole process. And this is an overview of our workflow component. So this includes first importing the data and running the model. And also we include all the possible row operations and transformations into this component, so that overall we only need to import a data and then we run the component, and after that we will get the results for analysis. And here's the part that we can customize for the modeling. So we can choose our fixed factor into the to put into the model and then to get customized results.
Next, I will go over the script that we developed. So this script, we use it to extract pre-test and post-test score from transaction level data. And then later we also converted this script into the workflow components that just showed for further use. So for this script, after we importing the data set, we will just do some filtering rules and then group by student and find each student's missing step. And then after finding the student's missing step, we will also only selected the entries with attempt 1, and then also computed students' pre-test scores and post-test scores. So in terms of the data we use, so Bernanke data set is the data sets that we did experiments last semester. We use it to run the baseline models and also generated the preliminary results. And then for DS5165 data sets on DataShop, this is also data sets that contain students' learning information and also has a column called is gaming. We use it to just did some experiments with the gaming factors. And then for DS3093 and 3151 on DataShop, it's a new data sets that we use for this semester. We use it to find the patterns in this data set and also use it for score extraction automation. So in terms of the evaluation, we used the mixed effects logistic regression model. So we computed the R square log likelihood, AIC and BIC for model comparison. For task design for mixed effects logistic regression, we used the whole data set for modeling and inference. We developed the following statistics for model comparisons and apply cross-validation. And then for the workflow components, we use different data sets to test whether it can fit into our pipeline and also adjust accordingly. So for our projects, there are also risks and challenges. There are processing risks, ethical risk, and product risk. So for processing risk, at the very beginning phase, we have some difficulties in encoding because there are like hundreds and millions of categories in one data set. And also we have software limitations. So later we transfer everything into GCP. And for ethical risk, the data set is very closely related to privacy and confidentiality. So we pay really careful attention to not sharing the data set to other third party. And for product risk, incorrect prediction might hinder students' learning process and also give like wrong decisions. So we also paid attention to this. In terms of the tool and dependency, we mainly use Python and R for programming and also use pandas and NumPy packages. And we basically mainly use our languages to build all the statistical models, specifically mixed effects regression model. So for this semester, there are 3 people joining our team. So we split the whole team into 2 subgroups in order to improve the efficiency. So for the first subgroup, which are me and Xingyu, we are mainly focusing on developing the IAFM model at the beginning phase and also testing with the gaming factors. And then in the later phase, we mainly focusing on the workflow component design and deployment, and also focusing on the writing the script for the score extraction automation.
So we 3 are divided into the second subgroup. So what do we do is mainly about extending the work of the previous semesters, including doing extra data analysis and like explore more model structures and to analyze the correlations between the different determining factors.
Okay, so here's our result section, and I will first give a quick recap on our first stage of the experiment. So in the first stage, we use the generalized linear mixed effect model to fit the data, and we use individual and KC as the random effects, and the opportunity that the number of times of a student answer the question as the predicted as a fixed effects, and the response is either correct or incorrect. And for this stage, we considering individual as a random effect. We have fitted 2 models. The first one use opportunity as a predictor. So the intercept we get from the model can serve as an estimation of the student's initial knowledge. And when we use the reverse opportunity as a predictor for model 2, here the reverse intercept can be used as an estimation of the student's competence at the end of the learning process. So here are the model stats for the first stage models. We can see that the model fits well on the Bernanke dataset with high R square and low AIC and BIC. And for the second dataset, the MANA 5615 is a smaller dataset, so it has a little bit lower R squares, but that's reasonable due to the dataset size. So with these 2 models, we have the intercepts estimations. So with the estimations of the initial knowledge and final stage knowledge, we proceed to stage 2.
So for stage 2, the main objective is to predict student post-test score with their pre-test scores. The question we want to answer is that stage 1 model which is generated help better predict the post-test score. The model is simpler then the stage 1 model is just linear regression models. And here's the result for the stage 2 model on the DS5615 datasets. And we can observe at for the first row, we only use the pre-test score to predict the post-test score. And for the especially the best performing is the third row. We use the pre-test score together with the model intercept from the stage 1 model to predict the post-test score. And we can observe that the AIC and BIC score both reduce, which indicates the model better explain the variations in the data, and also the F statistics is more significant.
So the p-values in that table, are you comparing to random or something?
I think the null hypothesis is that the data, the post-test score doesn't have any statistical influence on the post-test.
Okay, so all of these models are significant, but that third row is the one that's the best.
Yeah.
Okay, thanks.
And we specifically compare the first row with the third row with the pairwise ANOVA test. And so we can observe that the model with the stage 1 model outcome can give like lower residual sum of square. That indicates the intercept from the first model helps from the step 1 model helps the step 2 model better predict the data. And the p-value for the chi-square test suggests that the addition of the variable int IAFM, which is the intercept, has significant impact on the post-test score prediction.
We also explored an alternative stage 2 where we created a table with both pre-test score and post-test score in separate rows for each student. So in this stage, we trying to predict both the pre-test score and post-test score. And here we have 4 models. Model 1 use I first introduce the predictor for pre-test score and post-test. Use for trying to predict the pre-test score, we use the intercept. That's the estimation of the initial knowledge. And for prediction of post-test score, we use the reverse intercept. That's the estimation of final state knowledge and also the maximum opportunity of the student. And here we have 4 models. For model 1, we use for model 1 and 2, we use predictor 1 and 2 to predict the test score. These are 2 normal linear models. And for model 3 and 4, these are 2 one parameter fit model where we use fix the slope to be 1, and we are only training the intercept, that's the offset of the predictor. And we tried 2 ways to pre-process the data. So the first way is that we applied the sigmoid to the predictors because we want to treat the estimation of the intercepts and the maximum opportunity as a probability. And because our test score also falls in the range between 1 and 2. So in the first scenario, we applied sigmoid to the predictors and we use the original test scores. And in the second stage, we want to use a real value as the test score. So we applied a log odds to the test scores to transform it from a probability to the real values. And in this scenario, we found out 1 outlier detected. In the dataset, there's only 1 record with test score is equals to 0. So we use the minimum non-zero test score to replace that 0 entry to remove this outlier. So here are the model statistics for the sigmoid scenario. We may see that the model 1 is a little bit better than model 2, and model 3 is a little bit better than model 4, which indicates that predictor 1 might be a better predictor comparing to the predictor 2. That is, the estimation of knowledge might be better than the maximum opportunity. And similar patterns are also discovered in the log odds scenario. You can still see that the model 1 is better than model 2, but in general that the models in scenario 2 are not as well as the models in the sigmoid scenario because we can see that the R squares drops a little bit and AIC and BIC are a bit higher. So that's the general comparison, but the pattern is that the estimation of knowledge might perform better than the maximum opportunity as a predictor of the test scores. So we also generated scatter plots for the prediction of test scores and the original test scores. Like in model 3, we use the intercept as predictors. We can see that the knowledge estimation and the test scores in general, they have this a similar distribution, so which indicates that they might be a good predictor. But in the second graph here, the red ones are the results for the post test score, which we use at maximum opportunity as a predictor. So here the plot indicates that the students may all have tried many times to answer the question. The maximum opportunity are all very high in general, but it's not really match the pattern of their post-test score. So that means that higher opportunity may not indicate a higher or a good learning result at the end. So here are the scatter plots for the logouts, which indicate a similar pattern for both Model 3 and Model 2. We use these to verify our assumption and trying to compare to generate our analysis results. So that's the summary of alternative stage 2.
And besides fitting the models, we also study some primary factors that could influence student success. In the previous half of the semester, we conducted the correlation study between different variables, and we have found that the intercept and the intercept reverse have pretty high correlation. The intuition behind this is that the ranking of the students remains roughly the same across the whole semester. Students with better initial score are likely to end up with better final score. But this is not all the cases. Let's see the upper left triangle in this plot. Those students surpassed what we expected. And so we are particularly interested in studying these cases and trying to figure out what resulted in the better performance. For further analysis, we categorizing students into 3 groups: the overachievers who have surpassed our expectations, and by analogy, the underachievers and the norm achievers. Firstly, we calculated the difference between intercept reverse, which could be interpreted as the final knowledge, and subtracted by the predicted value of the intercept reverse. And then we set a threshold to divide the 3 groups. And we can see in the plot, the overachievers are colored in blue and the underachievers are colored in gray. Moving on, we want to explore the impact of the total opportunities, which is the number of questions a student has done. In the first place, we try to calculate the correlation between the total opportunity and the post-test score, and found the correlation is pretty weak. But it doesn't mean that doing more questions doesn't help with students' score. As we plot the box plot, we can to visualize the distribution of the total opportunities among different groups. We can find a clear pattern that the overachievers have significantly higher total opportunities than those underachievers. And next, we focus on analyzing students' learning gain across the whole semester. The learning gain is defined as the interface reverse subtracted by the intercept. And the orange line on this plot representing that the intercept reverse equals the intercept. We can see that the majority of the points are above this orange line, which indicates in most cases, the learning gain is positive. And the result is in line with our expectation. We can see in this box plot, there is distinct divergence among the 3 groups, and there is little overlap between those groups. And in the future, based on our work, we can deploy the script onto the LearnSphere as a component so that users can directly import the component for reuse. And it's also possible to investigate more features and conduct analytical analysis on the model results and gain more insights for our stakeholders. So that's pretty much for our presentation. We want to thank all our mentors for the help and providing the constructive feedback, and also thank all team members for the collaborative work. Thank you.
Great job, guys. So I didn't really know so much about LearnSphere until today. So I think you presented everything you did, which is great. But if you were going to sort of talk about your capstone project, like on a job interview, you definitely want to start by saying LearnSphere already exists. It already has a workflow, and that there was sort of this analytical gap. Okay. So the goal of your capstone was to basically do all of the preliminary formative research to figure out if that gap could be filled. And I think you did a lot of great work in that direction. But then you showed sort of some LearnSphere components, and I got this idea of, workflow, but you didn't end by saying that you had actually done anything. So how do you actually integrate these analytics into workflow? Do you just have R scripts or Python code, or how does that actually work? Anybody know?
So on LearnSphere, there are a lot of available like subcomponents. And the thing that we did is to first design the whole workflow structure according to our like our code, and then to like fit into the data set to see whether there are some issues with that. And so I think the LearnSphere can accept Java code for like new component design, and that is what we want to do for uploading our script to as a subcomponent.
So you have to figure out how to integrate your code with whatever those Java templates are for the different capabilities in the platform. Okay. So you definitely want to, if you revise this presentation because you're going to use it when you talk to people on the job hunt, make sure that you mention that, because that was kind of missing here. So it's a big part of your motivation, trying to augment an existing system, even though you were doing preliminary research, never actually got integrated. But you do need to sort of say a little bit about what that path is. And now that I understand what it is, I realize that it's too much for your capstone to worry about this, but it also seems like it would be a straightforward thing for somebody to do in the future. So I think one of the things that I think could be improved is you filled in all of the slides in the beginning, but it wasn't until later on that I knew sort of what the data sets were. It wasn't until your resource slide where you talked about that, and you never explained to us what courses those data came from. What the let's see, what was it? Knowledge components. What are knowledge components? So I think this talk would be perfect for somebody that already kind of knows LearnSphere and knows what those data sets are. But for this audience, I think we were left kind of wondering, are these undergraduates? Are these K-12 students? Are these graduate students? Are we talking about biology, physics, etc.? So you definitely want to be clearer for what the actual name is. And I think that because we didn't share that information, there's a remaining question in my mind about what generally the results are, right? So if you had said that these data sets are drawn from a variety of courses, a variety of users, so that this sort of model fitting that we're doing, we feel is going to be useful for any data set that will be analyzed by LearnSphere, I would be left with like a stronger impression. So how do you feel about the data that you used? Were they really drawn from a variety of learning contexts and a variety of student types, so that you feel comfortable about the generality of results? Or do you think that they really only represent kind of a narrow slice and more work will have to be done to kind of establish things.
I think the data are from a relatively small group and doesn't take the how can we generalize the data into consideration because the data is scraped from the online tutor system and the system may not be widely used by various students. Yeah,
but the sample that you got, was it from all of the students that are currently considered or only a subset of them?
Actually, I think that depends how the data set are collected, and we have the study on how they collect that data and from what scale they consider the students use this system.
Okay.
Yes, the data is from Carnegie Learning.
Mhm.
So I think it's mainly focusing on the like K-12 students for, yes, and the data set like we use for major analysis will be the math scores. So it will mainly focus on math, but like we also have a lot of other data sets, and the idea of having such workflow component is to like after we have that, we can apply different data sets on the same analysis and get more insights. But for this semester, we mainly the data set that we mainly use.
So did your mentors say something like, wow, let's do these data sets because these represent our most important category of users for the most important subject, math? Or do they say, oh, here's some data that we have? Because you could make an argument that what you did was actually exactly the right sample to start with, because it's sort of the most important.
So we were like given the data set at first for exploration, and we kept using that data set for like future analysis.
So I think these are some things that
I
you
clarify?
probably discuss with your mentors before you hand in the final report. Because I don't think it should be hard to formulate sort of a statement about each of these things mentioning, and it's going to strengthen the results, because right now you're giving the impression that you were very deeply embedded with your mentors in talking about the data and all of these interesting statistical analyses, but all of this other kind of more general framing of what you did is kind of missing. And you have a chance now to basically improve on this for the final report. And the final report should be something that any one of us can read without having any background knowledge of Carnegie. Well, I think those are the things I'm a little concerned about. But I think you have a chance to address those in the final report. And if you want to chat with me before you actually submit that, feel free to reach out. I'm happy to sort of take a look and let you know what I think covering the things that I'm concerned about. Okay, we have a couple minutes. Any questions from the audience?
I think the mentor is also on the point.
Okay, any mentor questions or comments?
I don't know if you can hear me.
Yeah, go ahead.
Can you guys go back to the slide with the orange line?
Yeah.
So the yeah, I was just trying to this is new since we last met, so I didn't get to fully process this, but the orange line is when is essentially the slope of 1, intercept of 0 line, right? So anything above that line indicates that
The positive.
right, the post-test scores are higher than the pre-test scores, right? Or the post-test predictions, I should say, are higher than the pre-test predictions.
Yes, the intercept.
Yeah, it would be nice to do something analogous for the actual pre and post data as well as these predictions.